All right. Well, cheers, everybody. Welcome. Welcome once again to Astronomy Daily Live. It's 2 hours UTC, and that means it's got to be time for some astronomy talk and space talk and science talk and general nerdy talking. So yeah, hope everybody's doing well out there. Everything is good here. So by the time I finished the session last night out at the scope, it was 23.4 degrees Fahrenheit. So it was cold. It was cold. And I, you know, when I was moving the telescope out, right, I've got the camera on the telescope now, right? So I bumped it, right, and that loosened the camera up, and I sort of was like, so I, took the camera off, put it back on, tried to, make sure everything was okay, but I actually realized early on in the session last night that the images weren't perfect. They weren't really bad. So it wasn't like a showstopper. But looking at them this morning and today, they're definitely not bad enough, to throw out. So I've gone ahead and started processing them, and hopefully over the next couple of days I'll be able to show you some results of that run. So yeah, pretty exciting. I'm just sort of mumbling and bumbling here to let folks come on in as they wish. So hope everybody's doing well out there. Very cool. Yeah, it's actually cloudy again here in southeastern Arizona. Again tonight here I'm 7 hours behind UTC. So while it's 2:03 UTC on the 13th of February 2019, here in my locality, hello, it's actually 7:03 p.m. on the 12th. So that is one of the things that when you get into astronomy, you have to sort of get your head around almost right away is the myriad of ways that time is measured. And so that's why I usually only speak in terms of UTC, that's a coordinated universal time, because in truth, there is only one time, and that's right now, right? Nobody is living in the future, and nobody's living in the past. We can travel there with our minds, right? Our minds, in sort of a certain sense, are sort of like time machines, right? We can move into the past, and we can actually locate ourselves in space and time. Whether that's real or not, I don't know. But it's kind of an interesting idea that the mind can be used as a time and space machine, because it certainly is, right? Anyway, so yeah, I'm just blabbing along here, letting people come on in, and I guess while we're doing that, why don't we say howdy to Bobby on the panel. Hey, what's going on?
Hey, what is going on to the what's up to the world? And hey, what's up, Tom? Everything we observe is in the past, says Tom. And welcome.
What did Tom say? Everything that we observe is in the past. Yeah, yeah. Well, you know, it's it's kind of hard, you know, to nail down here and now, right? Because you know, we are constantly in motion, right? And so, according to Heisenberg's uncertainty principle, you can't know an object's position and velocity at the same time, right? You can either know where it is or what its motion is, but you can't do both simultaneously. So you know, here and now is a really tough thing to hold on to. It's kind of like, you know, trying to grip water, right? It's like, you know, you squeeze onto it and it's just gone, right? So yeah, it's that kind of thing. So yeah, you know, everything we observe is in the past. I don't know, because, you know, when you make an observation in the present, you're observing it in the present. So yeah, I mean, you know, it gets really weird really fast, right? You know, when you start to actually think about these things, it you rapidly fall into a rabbit hole, right? Um, and that's why, you know, we have things like, you know, the tools of science and, you know, belief systems and all that to sort of, you know, allow us to at least have the the uh, um, the possibility of trying to grab onto these things, right? But I think that you know, there's a lot of things that are going to be, you know, completely out of reach, at least for a while, right? And I think that's a good thing. And Atta, yeah, I think you're right. Yeah. You know, I one of the greatest and you know, now um, I definitely have to preface this by saying that I am not a good student in sort of the normal sense of school, and that I wouldn't necessarily call myself a slow learner, but I have my own pace, right? And my pace is usually um, not the pace that, you know, the teacher sets, right? When you take a class like a college course, say, right? Um, they they go at some pace, and that pace is not mine. But there was at least one course that I took at the U of A, University of Arizona, that was really a blast, and it was a I think its number was physics 480. Was it 480? Yeah, physics 480, and this was a lab class, a physics lab class, and what it was, you know, this was definitely my thing. Again, it was probably a little bit too fast, but I was able to keep up with this. And what it was is we over the course of a semester, right? I think it was one semester. I think it was one semester, right? So what, 4 months, 3 months or something like that. I think we had to choose, I think we had to choose three or four experiments to do. And these were sort of the fundamental kind of experiments, right? So I think we did four. I think I did four. So I measured the velocity of light, right? I measured the ratio between the electron charge and the electron mass. I measured the charge of the electron, and there was a spectroscopy lab as well. And the coolest thing about this class, right, was that measuring the speed of light, right? What you got was the sheet of paper, right? It was a single sheet, and it basically said, measure the speed of light, and that's it, right? Now, we had access to lots of lab equipment, the professors wouldn't help us at all, right? They would watch us, and they would criticize us, but for the most part, they were supposed to be sort of hands off, right, and just sort of let us do our thing, right? And I think this single sheet of paper did have a few instructions. It's like, you might want to use this, and you might want to use that. You might want to do this, but we had to set up the entire experiment. We had to work out all the mathematics, right? We had to run the experiment. We had to collect the data. We had to, work the data and get the results. And in the end, we had to give a presentation to the class about what we did. So, I mean, that was absolutely great, right? And we had partners, right? So my partner and I were actually a perfect match, because he was absolutely brilliant at mathematics, right? It was just like, for him, it was like breathing, right? It was just super easy for him. And at the time, mathematics for me was tough, right? And it still is, to a certain extent. I don't think mathematics necessarily gets easy, but he was absolutely brilliant at math, right? Really good. But he could not set up an experiment or work with things at all. I mean, he was absolutely clueless, right? He saw our sort of the instructions, and he was like, I can't do this. I can't. Well, I'm pretty good at that kind of stuff, right? Given the chance and given enough time, to think about it and work it through and stuff, I can set up experiments. So between the two of us, right, I set up the experiments, collected all the data, did all that part. He did all the theoretical stuff, right? So between us two, we were a great team, great team. So, and that was one of the experiments that we did. I think it was the first one, was measuring the speed of light, and it's actually it's not really all that hard. It's not really all that hard to do it. You just have to, make sure that things are lined up right and all of that. And
I hate to break you up on it and stuff, but I'm not sure if there's any Chrome OS watchers out there. But is it just me, or is anybody that has Chrome OS is like a little slow time like Android apps? I don't know. I don't know. I'm trying to load Discord and it's not loading like it should.
Yeah, and you're sort of breaking up over our thing here too. So maybe something's going on your end. I'm not quite sure. Not quite sure.
Yeah, like I said, it is very slow. The Discord app for some whatever reason.
Okay. Yeah, you're definitely breaking up on this end too. So yeah. Do what you got to do there. So do what you got to do. Technical difficulties all the time. Anyway, so suffice it to say that Tom's mentioning of the speed of light.
Yeah, again, as I'm saying, sorry to break you again, but anybody that have their sub-70, you might have some technical concerns about the slowness of the Android app loading.
Okay. Yeah, you're definitely breaking up.
Ew.
You're breaking up, Bobby. You're breaking up.
And I'm having a little... Okay.
That's all right. He'll get it fixed. Bobby is a technical wizard. He can fix everything, for sure.
So you have a Chromebook as well, or you got like Windows or something? I got Chrome OS, and it's really taking a slow time loading the Discord app.
Yeah. Well, we will continue to figure that out for sure. So anyway, suffice it to say that that was a fun course, and it was great fun. The main instructor was this little tiny, I think he was Korean, I think. Just this little tiny guy, right? Little tiny guy, but to us, he was a giant, right? He would come in to the lab and he would just question us hard, right? Why are you doing that? And why are you doing that? And that's wrong, and that's wrong, and that's wrong. And I mean, he was doing all this, for a good reason, right? He was trying to teach us. And that was the nature of the lab, was that, we were supposed to do all this on our own. And so, we couldn't ask him for help, but he could criticize us. He could yell at us, the whole thing, right? And he did. And so, even though he was just a little guy, right? Just a little guy, we would cower you know, be like, oh man, here he comes. What's he going to do to us this time? And he always would. When I made my presentation on the Millikan drop experiment, the oil drop experiment, I had found that the charges that were on the individual oil drops were quantized, right? I could actually see that in my data. And so I made the claim that I could count the electrons on these drops. And he went berserk, right? It's like, there's no way that you can do that. And so I showed him, the data. This is right in front of the class, right? Live or right in front of the class, just like this, right? And he's just yelling at me about how that just isn't possible, right? And so I showed him the data, right? And the error bars were relatively small, and what I was seeing was actual quantized charges, right? And it's like, well, what else could it be, right? So yeah, I think he I don't know if he ever acquiesced and actually accepted the fact that my data was showing charges, quantized charges. But I think after a while, he's just sort of like, okay, whatever,
Yeah. So I'm not sure if everybody can hear me now, but on Chrome OS, I'm not sure if anybody's got that problem. For those people's watching it with your Chrome OS devices, but it's sluggish trying to get the Android apps for some whatever reason. I was trying to get the Discord Android app, and for some whatever reason it was so sluggish and stuff, and that can load with pure intent. So I guess it's like after the Chrome OS transitions from Chrome OS 71 to Chrome OS 72, you might see a little bit of super sluggish on the Android apps for sure.
Okay. Well, maybe you might want to check that out a little bit more and see if anybody else is having the same problem. If you just did an update, then it seems sort of likely to me that there's something wrong with the update, right? So yeah, hard to tell.
But like I said, Space TV, I was trying to load the Discord app, and it was like it'll load with pure intent before the update, but now it's not. For some reason, it's not loading at all.
Yeah. Hey there, Space TV. Nice to see you. Glad you could join this ever-growing group of crazy nerds here talking astronomy.
I'm gonna see what I can do after this live show, because just in case it's super sluggish.
Yeah. We can hang out a little bit right after this, if that'll help at all. So yeah, no problem. Yeah. No problemo. So yeah, last night's obsession went pretty well. It was a nice, beautiful, clear night. As I said, I sort of bumped the camera around, had to move it a little bit prior to the session, and that caused the pictures, the images, to be not quite as good as they could be, but I think they are good enough. And so yeah, I've started reducing that data and processing it and all. I've got to take my calibration data and get that all done, which I've already done. So I have my master flats, and I've actually gone through and reduced all the data, which is essentially 2 steps, right? I take the raw data, and well, okay. Before that, what I do is right at the end of the session, I took I think 20 dark images, 1 second long dark images, which means the shutter is on, right? I mean, it's not actually seeing any light or anything, so it's just measuring the sort of the thermal electronic response of the camera itself, and that's sort of a platform that all of the data sits on, right? And so the idea is, right, is that I want to remove that platform, right? I want it to go from up here, right? And so all that data is sitting on this platform, so it's up here. Well, I want to remove that platform, and then I want to flatten it, right? So I want to make the entire field nice and flat, and also nice and low, right? And so that's sort of a 2-step process. The first is to take these darks. So I took 20 1-second darks, and I take the average of those, right? And then that produces what's called a master dark, right? So then I take the raw data, right? The pictures of these stars in this case, and every single one of those, I took 600 images last night, 600 total. Every single one of those, I subtract the master dark from those, right? So I do that first, and that removes the platform, right? So now I'm down here. Then what I do is I take each one of those and I divide by the master flat. The master flat is a measurement of gain, right? So gain is the multiplicative factor, and so by dividing each of these pictures by the master flat, I flatten out that gain, right? Yeah, flat. There we go. So at the end of this, what's called data reduction, right? I've got 600 raw images. I've got 600 dark subtracted images, and I have 600 dark subtracted flattened images. And those
before Cosmic can continue, I was able to finally load the Discord app. I think there was like something that needs to be finalized. Like when you transition, when you do the update, it needs to like get the layer that does the Android on Chrome OS. It needs to like really get everything initialized for the first time, try to get everything into play.
Cool. So it seems to be working now?
Oh yeah, it's working with Jet now.
Yay. I knew you'd do it. Cool. Very, very cool. So in the end, I've got my dark subtracted, flattened pictures, and that is the science data. So now what I have to do, and this is the step that I still have to do, is now I have to take each of those 600 pictures, and I have to use one of those pictures as sort of a reference, right? So I usually pick the first one, right? I don't have to, but I can, right? And so I've got that first image that has, you know, my target star and my reference star, right? I've got two relatively bright stars in the field of view. And so what I do is I say, okay, here's the location of my target star. Here's the location of my reference star. Now, in the next image, I want to look for those two, right? Because of the tracking, they've probably moved a little bit, right? So my software will actually go and look for those two bright stars again, right? Once they find them, they'll take that second image and referencing the first one, they will shift that image, and if they have to, rotate it, right? And then they'll stack it, right? So that's sort of the next step there. Now that you know, the stacking part, I'm not going to have to necessarily do, but you know, my software will do that anyway, right? What I'm interested in, right, is actually measuring the brightness of my target star with respect to the reference star, because my target star, of course, is a variable star. It's a eclipsing binary star that was going through an eclipse yesterday, and that was sort of the whole point, right? And looking at the raw data, I can definitely tell that you know, it started off a little bit bright, got faint, and then brightened up again. But I have to take into account the atmospheric extinction, right? This object was actually rising, right? So it was getting higher and higher in the sky, which means its air mass was getting less and less and less. So the scattering of light was less and less and less. So it sort of automatically appears to be getting brighter, right? So I have to take that out first, and I'll be able to do that, you know, because I'll be able to measure exactly the same thing with the reference star, right? Now, there's a little bit of dependency on the actual color of these stars as to, you know, how fast they brighten up. But I'll be able to see that too. But the hope is that I'll actually be able to see this variable star go through its dimming and then brightening phase. But as I said, that's probably going to take a couple more days. I've got to fiddle with the code a little bit, and then run it, you know, make sure it works. I've got to take the extinction out, you know, all of that. So yeah, I'm at least a couple days out from doing that. But just looking at the raw data, I think everything looks pretty good. So I don't know how good, but we will see. We will definitely see. But yeah, you know, just sort of a preliminary look. It definitely looks like it about doubled in brightness from faintest to brightest. So I think that's about right. I think that's about right. But one cannot trust one's eyes. You have to look at the numbers, right? You have to look at the numbers. You have to let the processing. Well, you've got to make sure that the processing works, and then that ensures a relatively high level of trust. And once I'm able to trust that the processing is right, then I can look at the numbers and say, yep, absolutely, that is exactly what happened. So, but yeah, so hopefully in the next day or two here, I'll be able to make a report on that. And don't know what I'm going to do with that data yet. It sort of depends on what the quality of the data is. If it turns out to be, not too great, which I don't think it's going to be. I think it's going to be pretty good, I hope. Then yeah. Don't exactly know what I'm going to do with it yet. So, but I'll do something with it for sure. So I've got the hydrogen hydroxide here. Cheers, HOH, a nice, well-balanced molecules. Hope everybody's doing well. Cheers.
And I got my faucet water right here.
Excellent. Grab your consumable of choice. Sit back, relax, think all things space and astronomy. That's what this is for sure. So,
hey, those jugs that you used that you got for your hydrogen hydroxide?
The what that I got?
Yeah, that jug you got. We used to have some of those for sure.
Oh, these things?
Yeah.
Yeah. I don't know where I picked this up. I'm actually not really into plastic all that much, but for some reason this has just sort of become my go-to live stream mug. It's got a sufficient size, right? I do not like in any way, right, small mugs, right? I don't like them, right? It's like, you get a sip and that's all you get, right? So I like something sizable, right? And
I used to have the top of these. This was supposed to be like a coffee glass or something like that. But I've been using it as a way to drink faucet water out of.
There you go. Yeah. Innovation. So the only exception to that rule that I make is my coffee mug, and the only excuse I have for its tiny little size, right, is these super thick walls, right? Really nice thick walls. You hear that? Yeah.
Hey, we'll break it.
Yeah. No, I have dropped this multiple times, and I do not intentionally try to, right? But I've dropped this 4 or 5 times and nothing at all, right? Now I'm extremely careful with this thing, so I mean I'm not going to even try, right? Plus it's got some coffee in it still, so no way. But yeah, I go for the mugs, right? There we go. So there's a real mug, right? Yeah. Cool. All right. So, cool. What I thought that I would do that we haven't done in a little while is actually do a, and these usually extend for several live streams because there's so much to them. But I thought that we could at least start today doing a constellation of the day. I don't think we've done one of those in a little while, at least. I thought that would be fun. I always like to pull out my Burnham's Celestial Handbooks over there, and just sort of do a moderately complete perusal of stars and other non-stars that are located in these constellations, right? And they can be anything, right? I mean, I definitely like to find out a little bit about the individual stars that make up some of the constellations we see. But there are lots of other things too, right? There are galaxies, there are clusters, there are nebulae, there are binary stars, there's variable stars. The list goes on and on and on, right? Planetary nebulae, diffuse nebulae, globular clusters, open clusters. It just goes on and on and on, right? And I mean, people they literally spend lifetimes working on either some population of objects or even just a single object, right? Because most things in the universe are pretty amazing, right? And can be worthy of a lifetime of a very, very deep study. Those people usually become experts in that area, and they become sort of the go-to in terms of the rest of us trying to understand what's going on, right? So yeah, I think that we should do that, and I think Nightbot has been instructed to do that for us, to choose a random constellation. So I've got a list, right? I've got a list of the 88 constellations that are recognized by the International Astronomical Union. And I've got them in alphabetical order. So what I propose is that we ask Nightbot to choose our constellation, which is just going to be a number between 1 and 88. So let's go ahead and do that. I think I've got that set up here. We're going to find out. I'm going to do the command that I think it is. Maybe it isn't const. Maybe it's con. I don't remember. Oh, there it is. So constellation 46. 46. All right.
Yeah, so I wish I could have done the honors, but I forgot the command as well.
That's all right. That's all right. You might be able to do it next time. You just have to remember. That's all. So let's see. I've got the list up. I'm going to share my screen because I definitely don't want anybody to think that I'm playing favorites, because I'm not. All right, so here's my list.
Sometimes everybody plays the fool.
Well, I play the fool constantly, for sure. That's my favorite thing to play. So here's the list, right? And it's a list that's going to infinity. Isn't that cool? Look at that. Wow, that's great. Most people don't like this, and I don't understand why. I think it's great, right? Even the blinking cursor, right, is going to infinity. I think it's awesome. I see nothing weird or wrong with that at all. I think it's great. Anyway, so let's go to number 46. My number 46 is Leo. Wow. Ah, Leo.
Hey, that's my zodiac sign.
Oh, is it? Cool. Leo is a great constellation, and it's a huge constellation. It's a galaxy constellation, right? There are literally thousands
And a
and
zodiac
thousands.
sign.
And what else?
It's a zodiac sign.
It is. It is. And you know what that means is that the ecliptic, you know, that line that the sun seems to move through over the course of the year um, goes right through this constellation, right? The ecliptic is just the plane of the solar system, right? So if you sort of imagine the Earth and the sun, and the Earth is going around the sun in a flat plane, right? Well, that plane, if you project that plane onto our sky, it becomes the ecliptic. And it just so happens that the ecliptic actually passes through a number of constellations. In fact, at the moment, the ecliptic actually passes through 13 constellations, right? And that's because things are always moving up there, right? So nothing is steady, and over the course of time, the boundaries of the constellations have moved slightly, and so right now the constellation Ophiuchus uh, uh, also is one of the constellations that the ecliptic passes through. So that's just a little bit of trivia for your friends. When they say, you know, that there are 12 constellations in the zodiac, well, that's partially true and partially not true. Not anymore, at least. All right. Well, let's wow. So Leo is a big constellation for sure. Let's see. I'm going to go over here, and we're going to go up here. I'm going to stop sharing the screen. There we go. All right. Well, I'm going to go over here to my shelf, and I actually have my Burnham's.
And before you continue, maybe you should be doing like a little command thing that shows all the Nightbot's commands and stuff.
Oh, let me see if I can do that. I'm gonna have to think about that a little bit. I've got a kitty that is shading the light, so it's getting a little bit dark here, but she's just wandering around aimlessly, wondering what to do next. Anyway, I'm going to reach over here and grab my Burnham's Celestial Handbook. I've got my 2 Tesla books here that I've got to carefully pull off the shelf because I've got the covers of them off, and here's the 2 books. No, I haven't started reading them yet. I need to start, at least. I need to make some time.
Hey, got it.
What's that?
Yeah, there's a link for the Nightbot. It says check the chat.
Oh, cool. Okay, cool. Thanks, Tom. Yeah. Excellent. Excelente. All right, so I've also got this great book. This is a book that truly, honestly, every scientist should have. This is a great book. Excellent book. It has a CD in it. Huh. Okay. Don't know why. Anyway, fantastic book. Expensive book. I don't remember how much I paid for this book, but it was probably close to $100, I would say. But you know, it's an investment, right? And I've had this book for over 30 years now, right? Yes, Tom is a star for sure. I'm and yes, Tom, you noticed it still has the cover. Yeah. Now, how did that happen? Well, I think what you're witnessing is the difference between how a 20-plus-year-old treats his books and how a 10-plus-year-old treats his books. I think that's it. I think that's it. Because, yeah, by the time these were, in post-teenager hands, they were sort of in this kind of condition already. So I think that's sort of what you're seeing is general roughness of teenage hands, as opposed to somebody who actually had to lay down $100. And it's sort of like, am I just going to throw this on the floor and walk on it, or am I going to? I think the Mars command isn't working. Yeah, I've got to work on that one still. So yeah, I think that is sort of the difference. Is that this book, gets put up on a shelf. It doesn't necessarily get stepped on or walked on or anything else. But I dare say that this book has probably been used more than this one, right? In terms of opening it and using all the information in it for sure. So yeah, if you're ever able to grab a copy of this, get it. Bevington. Now this is the second edition, right? The which is I would say a slight improvement over the first edition. But if you can get either edition of these, get it, because it's some great stuff. I mean, it's all mathematical, of course, but it gets into how to actually analyze errors, how to process your data, how just on and on and on, right? Great stuff. So it looks like this is slightly out of focus. So I'm gonna hand palm it, pull it back. There we go. Pop. There we go. Yeah.
Why we're looking at physics while we're supposed to be looking at Leo?
Well, it's all the same thing, isn't it? All right. So Burnham's Celestial Handbook is another set of books that I would highly recommend. I don't think that they're in print anymore, but you can probably go to one of your local used bookstores and pick these up for a bargain, right? And they're a little outdated, a little bit, right? But not really all that much. What they lack is a lot more information is known now, right? But these books, in terms of getting yourself going and getting yourself started, are absolutely fantastic. So they come in three volumes, right? And yeah, these are in pretty rough shape. This is volume 3, right, which has absolutely no covers whatsoever. And these are ordered in Constellation order, alphabetical, right? So volume 3 goes from Pavo through Vulpecula, so it's not in this one. This is volume.
Two for sure.
Yeah, I think it's going to be in volume 2 also. So let me skip that one, and I'll show you volume 1 really quick. All right, there's volume 1, and you can see that the cover's off of this one, but it's got the side to it, and it's got the back, so that's not bad. But this is Andromeda through Cetus, right? So it's definitely not in this one. It's definitely in volume 2, right? And volume 2 has a side and it has a back. And this, do you see this here? Do you see this? This is new.
Damn that dumb cat.
This is new. Somebody got in here. Look at that. Look at that. Somebody got in here and was messing around a little too much. And what are you gonna do? You know. So what you're gonna do is you get some tape, right? You get some tape, and you tape things up, right? That's all. And try to be careful. That's all. Anyway, so
not bad, but if you got some Scotch tape,
yeah, some Scotch tape will work. No problem. No problem. So let's go to the entry for Leo. And what Burnham's Celestial Handbook does first is it lists all of the known binary or multiple star systems, right? So here it is. It starts on this page, right? And what they list is sort of a common name, right? So it could be a number. It could be some kind of Greek designation. The distance in arc seconds, right? The distance between like a pair of stars in arc seconds, right? The position angle, right? Which is, if you have two stars, right? You sort of designate one as the primary and one as the secondary. Well, if the position angle is 0 degrees, then the secondary is exactly north of the primary, right? And then I think how it goes is as that angle changes to the west, I think the position angle goes from 0 to 90 to 180 to 270 and then back to 0. Now, it could be the other way around. I forget exactly, right? So, when you observe a binary star, right, say that it's like this, right? Primary here, secondary here. The position angle there would be, what, around 135 degrees or so, right? Oh, my screen keeps blinking out, right? And, over the course of maybe years, say, you might actually observe that the position angle and the distance changes, right? And that's because, the secondary star is actually going around the primary star in some cases, right? So they also list the orbital period in years, right? Burnham's lists the magnitudes of the two stars or 3 stars or 4 stars or whatever it is. Make some very, very brief notes talking about, maybe the spectral type, um, other various notes, and then it gives the position of these binary stars in celestial coordinates. So the right ascension and declination. So that you sort of see at the top here, right? Here's a name, here's a distance, here's a position angle, years, magnitudes, some notes, and RA and dec, right? And the RA and dec is sort of encoded here, right? So how you have to read this, right, is that the right ascension in this case would be 6 hours, 20.7 minutes, and then positive 18 degrees, 21 minutes, right? So there is the right ascension, is these first 5 numbers, and then the declination is either going to be an N for north or an S for south, right? So north of the celestial equator or south of the celestial equator. Leo, of course, is north of the celestial equator. Sorry, that's going out of focus a little bit there. Don't know what to do about that. Anyway, so there's the first page of double or multiple stars. Here's page 2 and page 3. So quite a few. Here's page 4 and page 5. So that's all, those were all the known double and multiple stars in Leo when this book was published, right? Which was 30 years ago or so. So, now, just a wild guess, I would think that a listing now would be maybe 10 times that amount or so. I'm going to try to focus again here. Blam. There we go. All right. Cheers to focus. All right. Well, cool. So there's all of those. Then it lists all the known variable stars. And at this point, again, when this was written, there's all the variable stars that were known, right? Now we can actually go over to the AAVSO website and punch up the, in fact, let's go ahead and do that. I'm going to bookmark this with my owl lights here. So I'm going to go over to the AAVSO website, and we will look and see how many variable stars are now known to be in the constellation of Leo. Let's check that out. As I said, these constellations of the day usually take a few days to actually get through because there's so much. And with Leo, holy moly, I mean, I already know that there is a ton. There is a ton. So, all right, well, here, let me start at the AAVSO website, just in case folks haven't seen this before. So I'm going to share my screen, itch my leg, and share my screen at the same time. It's pretty talented. So I'm going to do that. I'm going to hide there. So we'll go over to aavso.org, right? The American Association of Variable Star Observers. And under variable stars, they have a variable star index. All right, so I'm going to go over there. And then we're just going to go to search, right? We're going to go to search, and we get this little form here. And we can choose the constellation, right? So again, this is in alphabetical order. So I'm just going to go down to Leo here. Well, there it is. And let's just pick, or just include, I'm going to zoom in a little bit here so everybody can see. Let's just pick the variables, right? Let's not do any of the suspected ones or the non-variable, just the variable stars, right? And let's order this by variable type, right? There are I think dozens of different kinds of variable stars. In fact, we can click on this just as a quick aside, and you can see the different kinds of variable stars, right? So there are two sort of primary types, the extrinsic and the intrinsic. But then under those are these subtypes, right? And then under those are subtypes, right? So here's all the different kinds of variable stars, right? It just goes on and on and on. You know, we humans like to categorize things, but you know, there's so much out there, and there's so much, you know, so many differences that you know, there's just a lot of categories. So yeah, these are all the different kinds of variable stars. There's just dozens of different kinds, right? And they all have, you know, pretty specific characteristics, right? Which, you know, distinguish them between types. So yeah, just on and on and on here, right? Okay, but that's not what we're after. But I'm going to order this by variable type, just so you can sort of see, you know, not only how many variable stars are known now in this single constellation, right? But all the different types as well, right? So that's all I'm going to do, is just do you know, the variable stars in the constellation of Leo, order by variable type. And so you remember Burnham's listed one page, right? It was a full page, right? But it was just one page. Now watch this. Check this out. So here is the variable star type, right? Here's its name. This is some kind of a some kind of other name, right? It's just another name. Let me zoom out a little bit, because it doesn't look like we're seeing this whole thing here. And if you excuse me just for a moment, I have to do my duty and let a kitty out of here before she explodes. All right, so hold on just a sec. Hold on. Come on, you want out? Let's go out. Come on, hey. Hey, you want it out? She looks at me like, what? Did I say that? Okay, so here's the name, the celestial coordinates, the constellation, the type of variable it is, the period in days, and then brightness range, the magnitude range, right? So here, let's just go through these, and you can see how many variable stars are in this one constellation, right? It just goes on and on and on. Look at that. There's hundreds of them, right? Hundreds and hundreds and hundreds and hundreds and hundreds. All
they must have really did a lot for that index.
Well, you know, this is what surveys allow us to do, is identify and realize that, you know, there's a lot of stuff out there. There's a lot of stuff, right? So I'm about a quarter of the way through the list here, right? Just goes on and on and on and on and on and on and on, right? I'm scrolling down. I'm actually going to grab this and move a little bit faster, right? So as you can see, a lot of these have sort of the same first names, right? And these are surveys, right? There was a linear survey. There was a CSS survey. There's a GSC here. You know, these are all surveys that were looking for variable stars of some kind, you know, with some kind of characteristic. And I mean, I don't think we've seen anything yet, right? Because look, if you look at the magnitudes here, right, these are all, you know, relatively speaking these days, these are all pretty bright, right? I mean, 18th is getting a little faint, but I mean, you know, we have survey telescopes now that can easily go down to 21st or 22nd, right? Gaia goes down to 22nd magnitude, right? And so we're going to find more of these things, right? It's all we have to do is look. You know, the data is all there. So there are, I dare say, in you know, surveys like Gaia and Pan-STARRS and all that, there are variable stars that are still to be discovered. Somebody needs to go out and discover them. So yeah, it just goes on and on and on. I'm about halfway through now, right? It just goes on and on and on and on.
Thank you.
And on. Yes. All those photons make me sneeze too. So there's sort of the updated list of all the variable stars in the constellation of Leo. And I don't know if it gives a total here. Yeah, 3,235. So pretty good, right? This list alone, right, is lifetimes of work, right? Lifetimes of work. You know, if you were to observe each one of these and get a light curve, you know, you probably want at least a few of them, you know, to make sure that you're right. So this is lifetimes of work here, right? So yeah, that's what these surveys sort of allow us to do. And like I said, we ain't seen nothing yet. Wait until surveys like the LSST, the large synoptic survey telescope. Wait till that thing comes online. It's going to be insane. Like I said, I'm thinking that this number is going to increase by at least a factor of 10. So yeah, because I mean, there's a lot of stuff out there. There's a lot of stars, lots and lots of stars. You know, and most stars are variable in one way, you know, or in some way, right? Anyway, so yeah, I think that's just absolutely amazing. Absolutely amazing. All right, well, let's see. Let's do one more thing, or at least a couple more things before I go. I'm noticing that we are past time. Hey there, Twin Crow. Nice to see you. Yes, everything's good. Everything's good. We're starting what is usually a multi-day investigation of the constellation Leo. in this case, we randomly chose that. So now
Hey,
we're just gonna.
I also had to refresh the chat. So, hey, what's up, Twin Crow? And wait a lot, Otto.
Yeah. See you later, Atta. If you're still there, see you later. So yeah, with these constellations, we usually take several days, and we just sort of slowly go through them, look and see if there's anything interesting. Uh, you know, focus on a few things. We're we're just looking at a list of all the variable stars that are in the constellation of Leo, that have been identified by various surveys and lots of observers and all of that. And yeah, at least according to the American Association of Variable Star Observers, there are 3,235 right now, and that number is bound to go up for sure. So yeah, let's do a couple more things here before I let you go. I'm going to go back to Burnham's, and after the variable star list, right? Burnham's lists all the non-stellar objects. So this can be galaxies, clusters, nebulae, those kinds of things. And like I said right at the beginning of this, Leo is a constellation full of galaxies, full of galaxies. Now, when Burnham's was published, this is the list of non-stellar objects that we knew of within the constellation of Leo. And as you can see here, right, it's got the NGC number, the New General Catalog number. I know that's kind of hard to see, sorry. There we go. Here's another name for it, right? Here is the object type, and as you can see, all these are galaxies, right? All these are galaxies. Here's some notes about, what kind of galaxy it is, how bright it is, its size, some notes about what it looks like, and again, the position of it in the sky, right? So there's page 1. So here's page 2 and 3. Again, all galaxies, right? Now, every single one of these galaxies can be seen with your own eye, given the right size of telescope. Some of these are getting pretty faint, and I'm going to try to focus this thing again. Bam. Some of these are getting a little bit faint, but most of these you will be able to see with about a 12-inch telescope or so. So, this size of a telescope, which is 8 inches, I'm not going to be able to see all of these, but I'll be able to see most of them. So, and then here's page 4, right, which again is all galaxies, right? So then what Burnham's does is it goes through and talks about some of the main stars, right? It'll talk about Alpha Leo, which is also known as Regulus. And it gives the history, how it was named, when it was first observed. This camera is really being a pain tonight. It's just trying. It's trying to do its best, but it's not doing very well. So yeah, lots of history. It's got little coins with Leo the Lion on it there. It's talking about Beta Leo and Gamma Leonis. of course, the Leonid meteor shower, which is a famous meteor shower that can be quite spectacular. I think the Leonids are, I want to say in November, but I don't remember exactly. We can probably find that out. And then it'll talk about at least some of the variable stars, right? And it shows light curves, right? So this is brightness versus time, right? So you can see, in this case, this is a star called R Leonis, the letter R. And as you can see, it gets fainter and then brighter and then fainter and then brighter. But it's not always the same, right? This is a little bit fainter than this fainter, right? And this is a little bit brighter than that brighter. So, you know, even sort of a regular thing like that, there are subtle differences each and every time. And it's those changes, it's the differences that can tell us really, really interesting things about these stars. So then once it talks about any interesting binary stars and the interesting variable stars, it will talk about lots of interesting non-stellar objects. And in this case, because it's the constellation Leo, it's talking about galaxies, right? So it shows a bunch, well, it talks about several galaxies. And there are, I think there are, I want to say that there are 4 Messier objects in the constellation of Leo. There's M65, M66, and then M95 and M96. I think that's it. There might be more, but you know, they show, you know, some photographs of them here, which you know, are you know, for the time, these were pretty good shots, right? Here's M6. I think this is M66, M65, and then there's another one up here, which isn't a Messier number, it's an NGC number. So Charles Messier missed that one, didn't see it. It's fainter than these two, so that's understandable. Here's a blow-up of M66, right? It's a nice spiral galaxy there. Sort of got a little bit of a bar through it.
Leo Nebula.
Leo Nebula? I'm not aware of a Leo Nebula. I don't think that there is, at least you know, the common term for a nebula is you know, a cloud of gas and dust that is either glowing or reflecting light. And I don't think, I mean, I could be wrong about this, so don't quote me or anything, but I don't think that there are any nebulae in Leo. But let's try to find out. So remind me of that, Bobby, and we'll you know, we'll keep our eyes out for it, because I mean, hey, I don't know all these things. No way, not a chance. So yeah, they talk about M95 and M96. Right, here's M95. That's a nice, it's got a nice bar through it, and then almost like a ring, right? And then here's M96 down here. So these were, at the time, really, really, really great photographs, right? Here's a cluster of galaxies, right? You can see all of them here. So yeah, so I think probably the last thing that I want to do, just really, really quick, and we will end on this, is let's go over to Wikipedia they usually have a really, really, really good picture of the constellation itself, right? I mean, it's a graphic, but it sort of, it shows the outline of the constellation and some of the major stars and objects. So I'm going to run over and grab that really quick. This is a pretty large constellation, so it is definitely going to take us quite a while to get through the sky, which I don't mind. I mean, that's great, right? So let's see. This is the let's see which. This is the. I'm trying to see. So this is the 12th largest galaxy in the sky, right? 947 square degrees. It's actually got 5 Messier objects in it. So I've missed one. Let's see if it'll, don't remember what the other one is. Oh, M105, of course. Yeah. Okay, so I'm gonna zoom in on this really quick, because I know that time is running away from us here. And there's no need to hurry, right? Because we've got tomorrow and the next day and the next day. So I'm absolutely in no hurry whatsoever, but I do respect your time. And so I don't like this to go necessarily too long. So I'm going to hide that, and I'm going to go over here. We'll just take a quick look at the outline of this constellation, and then we'll end it for today. So actually, Leo, if you go out at sunset right now, when it gets dark, right, and look to your east, you will actually see Leo rising right now, this time of year. Leo is rising. So when it's clear at your location, go out and take a look, see if you can see it. It's kind of hard to see here, but there is kind of a relatively easy pattern here to see. It sort of looks like a backwards question mark, with Regulus being the brightest one right at the bottom, and then this loop of stars here that comes around and then goes down, right? So go out and see if you can see this. And as you can see, the ecliptic goes right through this constellation, which means it's one of the constellations in the zodiac. So yeah, the only thing that it doesn't list here is M95, and M95 is right next to M96. So I'm not quite sure why they're not showing it here on this chart, but they're not. But yeah, so let's see, it goes from about 9 hours and 20 minutes all the way over to 12 hours, right? So this is like more than 2.5 hours of right ascension, east and west. And then it goes all the way down to below the celestial equator here at 0, right? Goes all the way down to what, about -6 or so, and then all the way up to like what, about +33 or so up here. So yeah, I mean, this is one of the constellations where it's not square, right? It's got all these weird sides to it and stuff. And these borders are discussed and you're decided upon by committees of the International Astronomical Union, and I think are almost always subject to change. Historically, these borders were probably different, right? So and will they change again? Yeah, they probably will. But so usually how these names go, at least the Greek letters here, is that the brightest star in the constellation is Alpha, right? I'll zoom in here a little bit for you. And that is the case here. The brightest star in the constellation of Leo is Alpha Leo, also known as Regulus, also known as probably a bunch of other names, right? Bunch of other names. The nebula over here is the second brightest star, and at least I think maybe Gamma. It's kind of hard to tell. They normally in charts, the larger the dot, the brighter the star, right? So all these small dots here are really, really faint, and these big dots are bright, right? But it's almost looking to me like Gamma might be brighter than Beta. Kind of hard to tell. We'll have to find out, right? But anyway, so yeah, there's the constellation. You can sort of see where it is. It's what, west of Virgo, north of Sextans, south of Leo Minor and Ursa Major. Craters down here. Yeah. So, oh, and they actually show the magnitudes here, right? So these little dots are 6th magnitude, which is about the limit as to what our eyes can see at a really, really, really dark site. And then, as you can see, there aren't. I mean, Regulus looks like it's somewhere between a 1st and 2nd magnitude star, right? So the smaller the number, the brighter the star. That's just how the astronomical magnitudes are. It's sort of backwards to logic, but a lot of things in astronomy and science are like that. So it's just something that you have to get used to, you have to be aware of, and after a little while, it just sort of becomes second nature. And there is an explanation for all that. So yeah, that's something that you might want to investigate a little bit. So, all right, everybody, it is definitely way past time. So I'm going to end this live stream for today. Definitely, I will be here once again tomorrow, same time, same place, 2 hours UTC. I think it's supposed to be cloudy the next few days, so I will definitely be in here. Yeah, and let's continue the dive into the constellation of Leo. It's a big constellation. Lots and lots and lots of things to investigate and to find out about, and we're going to just barely skim just the surface, right? There is so much that it would take lifetimes just to sort of investigate all these things, much less study them and learn about them and all of that. Yeah, no. So we're just going to skim, just a few things right off the top. If there's anything interesting at all, let me know, because I'll definitely want to focus on anything that you folks want to focus on. But usually things catch my eye too. So we can go either way with that. So all right. Well, Well, cool. I'm going to get out of here for now. So have a great evening, a great day. Don't get dizzy. This Earth is spinning at 1,000 miles per hour. Right now, we are all spinning around at about 1,000 miles an hour. Right. So hold on to your hats. Right. They're not. It's a smooth ride. Right. It's a smooth ride, and we're pretty grounded here. Right. So I don't think that we're going to fly off or anything. I don't think so. Haven't yet, at least. So I think you can say with confidence that we probably won't. So, but we are moving at a dizzying speed, and we don't even know it, right? But it's just like moving in a car, right? When you're sitting in the car, you're not moving, right? Relative to the car, right? So it's the same kind of thing. I'm sitting here on Earth. Yes, live long and prosper. All right, cool. All right, I'm gonna get out of here.
Live long and prosper.
Yes, sir. All right, well, take care, everybody. I will see you in a little less than one of those spins, right? In a little less than 22 and a half hours from now. All right, take care, everybody. Peace, cheers, and all that. I will see you later. Bye.